All right, welcome to If You Can't Open It, You Don't Own It. Does anybody know where that title comes from? It's not original with me. So that's actually a saying in the hardware hacking industry, which is if you can't get in the box and get to the hardware, you don't own the hardware. So once you get in, you'd be surprised the links that a vendor will go to prevent you from just getting into the box. I mean, they'll seal it, they'll seal the board, they'll seal all sorts of stuff, just trying to keep you out of it. So I had kind of an interesting thing happen. The guy that brought me down this track, I come from the embedded world, and one day I got a call from my wife. She says, well, the printer's having problems. So I said, okay, shut it down. I'll look at it when I get home. So I bring the printer up and I bring her machine up, and sure enough, I can't print. And then I noticed that there is a lot of traffic on the switch. And so I said, okay, well, what were you doing today when the printer started messing up? And she said, well, I was doing research at this university. And it wasn't a sketchy university. It was one that you normally go and do this kind of research at. And so I thought, okay, well, first let me find out what the traffic is about. So I pull it off the network so it can't get out of the house. And then I'll deal with the printer later, and I shut the printer off. And all the traffic stops. I thought, okay, this is kind of weird. So I turn the printer back on. All the traffic starts up again. And so I put Wireshark in the loop, and I'm looking at where the traffic is going. I'm finding IP addresses that something within our environment is trying to connect up to. I go out through another PC. I find out, oh yeah, these are actually sort of sketchy IP addresses they think are actually proxy servers going to some sort of nation state. And I won't mention it, doesn't matter which one. And by the time I got done with the analysis, it took me a couple of hours to sort of unravel this. What had happened was she'd gone to this university and somebody had run a water holing attack against the university website. So what happened is she would connect up, it'd get on her box, and it would go and replace the firmware on her printer because it could identify the printer and it would replace it with a different piece of firmware. And that's why the printer didn't work. They didn't get it quite right. And if you hadn't printed, you wouldn't have known this. And the printer would have just been sitting there the entire time looking at every machine that it could get and then just starting to take stuff off and ship it to these IP addresses. And that's sort of an example of what happens when you have what is a low priority system that gets attacked, that now it's inside and it has the ability to do things in your higher priority systems because now it's now moving laterally within your system. So I wound up throwing her hard drive away along with the printer, bought a new one and rebuilt it, but it was actually a pretty elegant attack because you had no way of knowing that it was coming. And if you don't print, you're not going to know there's a problem. And if you print and you have a problem, you're going to blame the printer. You're not going to think somebody's gotten into your environment. So it was actually a pretty cool attack. And that's part of what we're going to talk about today is hardware and how hardware attacks can inform how attacks go against our software. So I'm going to do a quick review for those. There are a few people who weren't here in the threat hunting program yesterday, so I'm going to do just a very basic review. So we talked about the intrusion kill chains from Lockheed Martin. If you want to go deeper into this, go watch the video from yesterday's talk. We have reconnaissance, that's either people or technology, then weaponization. Once we know how we want to attack a system, we're going to develop the weapons we're going to use against them. Delivery can be USB, email, direct connect, any way that you can get into their system, going against their perimeter security if it's unpatched. Exploitation is that you're exploiting a known set of vulnerabilities within their environment to be able to move laterally and to move into other systems. Then installation is I'm going to actually get my beachhead. Once I've penetrated into a system, I'm going to use that as a jumping off point into the rest of their systems. Command and control is just simply now I'm talking to an upstream server. So now I can actually send it instructions as to what to do, what I want, and where to go. And then action on objectives is that's when you own the system, you're moving freely within their environment, and you're doing whatever it is that you came there for. You're grabbing data, source code, whatever it is that you're looking for. So threat hunting is about understanding the nature of the threats, but it's also understanding the nature of the attackers. So our software, our hardware, whatever it is that you're building, runs in areas where you have darkness, isolation, insecurity, and invulnerability. We all do this. We've done it since we were kids. We know when we cross a street, you're threat hunting about the cars. When you're driving down a highway and you're coming to an intersection, when someone's coming up behind you, you're threat hunting. Are they going to do what they should do, or do I have to worry about them doing something stupid? What we do in threat hunting is it forces us to focus on the system as a whole and we follow the data. And that's pretty much universal, whether it's software or hardware. We are operating now in a zero trust environment, so even inside your environments on your hardware, it's zero trust. No matter what you have running, you can't assume that just because you're inside this nice box that you have a trusted environment. The exfiltration is now becoming more important than infiltration. I think we sort of have this idea that we've lost the battle, that they're going to get in some way. Somebody will make a mistake. They won't patch a box. They'll leave something open that they shouldn't. They'll click on a link they shouldn't. They're going to get in. But the big thing is the complexity. So complexity is the enemy of our systems. The more complex a system is, the harder it is to reason about. That's when you get emergent behavior. That's one of the reasons why we document things like this, is because once you have to document it, you begin to understand just how complex your system really is. And then all exploits are bugs, but not all bugs are exploitable. So it depends on how close they are to an attack surface, and we went through that in yesterday's program. So let's talk about the dark art of hardware hacking. It sounds very dramatic, but it actually, if you've ever done it, it really is sort of a dark art because it involves a lot of different skills. It's a lot of fun if you do it. One thing you have to remember, though, the DCMA does have some penalties for cracking open other people's boxes and hacking them. So you have to figure out what your local laws are, but you can get into trouble for doing that, so I'm not going to advocate that you do this. This is just a lot of research from the years that I've had actually coming from the other side, is trying to protect hardware from exactly these kinds of penetrations. So let's talk about Shadowhammer. Shadowhammer was a really neat attack. It actually came last year. What they did is they they compromised ASUS's networks. Then they went in and somewhere before either at the point at which the binary is cut or they got into the source code, they added their own malware. So they wanted their own payload in there. And this is for the firmware for their PCs. But what was really neat about this attack is they got it before the binaries were signed. So if you get it before the binaries are signed, you're golden. You're in their software at that point. So they pushed this out to about 500,000 computers, and what it does once it gets down there is it infects the PC, and so this is in the firmware of the PC. It opens up a backdoor and allows them to move around in the system at will. What was really interesting about this one, though, sorry, is that there were 500,000 computers infected, but they were only looking for 600 MAC addresses. So they had that kind of intelligence of, we're not just broadcasting this out to everybody because we don't care about everybody. We've got this very set, and it's one thing to go after IP addresses, which are much easier to source, but these were going after the hardware addresses on the NIC of the box. And so right now there's sort of, I'm sure the intelligence community has already figured out where this came from and what they were after, because these 600 MAC addresses give you an idea of who it is and where they came from. But this leads to a conversation about roots of trust. And we don't hear about it. Has anybody ever heard that term used either in hardware or software? Yeah, okay, so one person has heard it. So for those in the back, roots of trust are highly reliable hardware, firmware, and software components that perform specific critical security functions. Because roots of trust are inherently trusted, they must be secure by design. As such, many roots of trust are implemented in hardware, which is true, because it's much harder to hack hardware than it is to hack software, so that malware cannot tamper with the functions they provide. That's unfortunately becoming less true, and that's where we got to with Shadowhammer. Roots of trust provide a firm foundation from which to build security and trust. And this comes from NIST. It's a pretty basic, it's a good definition. I like it as far as roots of trust. It doesn't go as far as we need to go, because what we need to do is look at the trust landscape. So here is just a basic system. We have our applications layer, which is sitting on top of an operating system, which is then sitting on top of a hardware. And implicitly, we trust the layers below. We don't really get a choice in the matter, but we do feel very comfortable in trusting it. So our software trusts the operating system, and the operating system trusts the hardware that it's running on. Everything comes up, it boots, it's nice, everything is fine. We have an assumption that everything is that out of focus? Okay. There you go, that's better. Awesome. Thank you. And when we think about roots of trust, that trust is organic. It means it changes. It's not something that we set in place, but it is something that changes over time, depending on what you're loading in the system. So in this case, where we're looking at a root of trust, it's always the lowest layer that has the highest trust. And that makes sense from not only the perspective of you don't have a choice but to trust the layers below you, but it also is that as you go down in here, it's much harder, it's easier to penetrate up here than it is to penetrate down there. So our theory is that it has the smallest attack surface, it's farthest from the attack points, which is going to be in the software or the operating system. It's harder to understand, which is generally true. And the attack vectors are harder to realize because it's farther away from the places where you can actually go directly into it. But what layer here is missing? We talked about it 2 slides ago. The firmware. More importantly, it's where the firmware comes from. So if you have the firmware that's up at ASUS's environment, and they come in and they get into ASUS's environment, they have now penetrated all the way down at the very bottom. We don't think about the ASUS firmware, and we don't think about the software company that is actually generating the firmware that runs this hardware. So what happens when we have broken trust? So we undermine the layers above. The deeper we can get in, the more of those layers are undermined. They're built on top of that. And in this case, this is actually a case where we have where the security is undermined. Now this is a Tesla vehicle, and this was an actual attack. This was done by researchers, not by state actors or anything like that, but it could easily have been. What they did is they launch a remote communication attack, because what is the other thing that a Tesla is doing besides driving the car or you have your infotainment? It's talking to the upstream servers. That's where you get the updates to firmware. That's where you're sending diagnostics back to the company. Airplanes at this point have a satellite system. So every modern aircraft has a satellite system that is constantly sending their ACAR messages back to the airline. Part of it is they're sending engine performance data back because that's the most important piece of the aircraft. But the other thing is that's how they know when it's going to arrive, because they get position reports even if they're out over the Atlantic or the Pacific and you actually don't have them on radar anywhere. It's that satellite tracking that tells them this is exactly when we intend to land. In this case, there was a remote communications attack that somehow went into the infotainment system. And from the infotainment system, they were able to run a privilege escalation attack against the main system that they had here, which is, so when we build a vehicle, whether it's an airplane or a car, we've got the part of the computer systems that's there to get you from point A to point B, and then there's the infotainment system. And if you go look at the cars and the amount of code, you'll find out that the infotainment system is more complicated and has more code than the parts of the computer systems that are actually designed to get you from point A to point B, which was the original use of the vehicle. So what they did was when they designed it, they actually wound up sharing a bus. So the infotainment system shares the same bus system, same bus architecture as the piece of the car that actually drives it. So what they did was they came in and they placed SoC as a system on a chip. They came in and they replaced the firmware. So they go in from a low priority system, they migrate to a high priority system, and now they have the ability to send messages directly to the vehicle, which would allow it to chain. So now what we have is a broken trust, not because somebody's penetrated the lower support, but because we've mixed trust models here. We've got something that's got a low trust that has the ability to talk to something that is a high trust because they use the same bus architecture. So one of the things that we're starting to see a lot more in hardware, and this affects us because of the way systems boot up, is this secure boot system. So this phase 0, which is the bootloader, has it's an immutable bootloader. So it's always going to go to the same spot in order to start the bootloader. You can't redirect it to a different place. So in this case, this bootloader is going to bootstrap right here with into an immutable location, which all the rest of this becomes what we call a chain of trust, because each one is encrypted and the keys from one allow you to open up the next step. And this allows us to have a secure boot that goes from the BIOS to the OS loader to loading the image and then beginning to load our applications to bring the system fully up. And what this does is we'll talk a little here in a little minute about why it's important to know the boot process. Can I interrupt the boot process? Can I change the boot process? So if anybody's done hardware, you'll recognize U-boot. If you ever go in and look at a piece of your, it's amazing when you look at a piece of home equipment like an appliance, if you can plug into the right place, you can watch the boot sequence come up. And you'll see all the same stuff that you're used to using. So what we're doing here is we start with the lowest level possible, which is the boot, in order to make sure that what we have coming up in the system is secure as we can make it. But we've also changed the way the hardware works. This piece over here, this secure world, used to not exist. We trusted the CPU implicitly because it was as far away from tampering as possible. It's hardware. We don't think you can get to it, but what we've realized is people have changed firmware as we've learned how to hack hardware, and much easier. As that's become much easier, we've had to actually create new types of security within a PC. So this is an ARM processor, and one of the things that this secure side does is it's run in isolation. So there are some, they call it trust zones, so there are some APIs which allow them to access some of the facilities within it, but the chip now relies on an entire different part of itself that runs in isolation, which allows you to get things like cryptographic services, anti-tamper services. There's an identity that goes to that. And some of these identities, which is with the boards, actually comes from manufacturing. So the manufacturing tolerances will vary, and what happens is when you put a board together and if you take a look at it, it's almost like a CRC because of the manufacturing variances. You get almost a chip that has its own unique identity. So whether it's at the board level or the chip level, none are going to be exactly the same, and that sort of becomes the identity. So what we're trying to do in the hardware world is make sure that we can have these kinds of things running in isolation that we can use to help bring up our systems and make them more secure. So let's talk about software. So we explicitly trust a lot of things. So we operate up here in C++. And we trust things like, because we don't have a choice, the operating system, the firmware that's on the hardware itself. But we also implicitly trust a lot of things that we don't think about. For example, the permission system. We rely on that to work correctly. If we set the expectation that this particular piece is going to have this set of permissions, well, what happens if those permissions change? Because we're relying on those to keep other people out of that part of the system. The file ACL is the same thing. The CPU architecture. This is where you get things like caching and you get the branch prediction that the side channel attacks for Meltdown and Spectre took advantage of. That's 20 years of our processor technology and improvements in performance. Communications pathways. We assume Wi-Fi is going to be secure. It's not. WPA has already been broken. WPA2 has been compromised already. And then the update system. We're assuming that the ASUSes of the world don't have this problem down here. So we have this implicit trust model that goes from the top to the bottom. The problem is that for us, it's actually mostly bad news. We can trust the hardware, but we don't own it. We can trust the kernel, but we don't have any control over the kernel. We can trust the constraints in the system, but those can be bypassed. We've seen that a lot of times. We can trust the libraries that we're using, but those can be replaced. There are specific attacks for replacing the libraries with something else. We can trust the update system, but those can be breached. We just saw that. We can trust the transport layers, but those can be broken. So most of what we as technologists trust, either explicitly or implicitly, is things that we really don't have any control over. So what can we trust? Any guesses? No one. I trust me. So you can trust what you control. So you can trust what you compile, so the code you write, the systems you architect. You can trust the libraries that you use because you get that choice as to use them or not. You can trust who and what you connect with. So if you're talking to someone else on the other side, you can trust either whether you validate them or not. And you can trust what you hold in memory and how long that you hold it there. So One of the first rules is don't mix trust modes. That's the lesson from the Tesla. You have a low priority system or a low trust system called the infotainment that we really don't care about its security. And then you have something that's very high security, which is the piece that drives the car. In our software, when we have a binary or an application that has multiple trust modes, the best thing to do is break those up. Make it so that if you've got something that is a low priority, put it in a low priority process, but don't let it have contact with the higher priority processes. Because if I can penetrate the low priority, I can privilege escalate up into the high ones. Sign your code and verify it at startup. We do the first one a lot. Lots of people sign their codes, but then when they go in and the code comes up, does the binary actually check to make sure that the signatures match? If you don't, there's no reason to sign it. And then encrypt your traffic even if the transport layer is already encrypted. Go ahead and encrypt your traffic over Wi-Fi. You have no control over whether that Wi-Fi that it's talking across or the network is going to be going into are in any way secure. So if you haven't encrypted it in your systems, then you're at the mercy of their mistakes or at the mercy of whatever encryption they have on there. So double up on your encryption when you're sending it. Libraries. Now I'll hear lots of feedback from this. This is about not trusting open source. It's not that I'm saying don't trust open source. What I'm saying is don't trust open source code that you didn't write. You don't know who the owners are. You don't know if it's been tested, and you haven't code reviewed it. And the reason why, and we're going to get to one here later, we're going to get to the reason why is if you don't know how that code behaves, and you're baking it into your software, you own it. You may not have written it, you may not know everything that it does, but you're going to own whatever that thing does. So on these libraries that we are using, and there are a lot of them, you need to know what it is that you're putting in because their vulnerabilities become your vulnerabilities, and if they're misbehaving, that's something you get to deal with. So we'll talk a little bit more about that when we get to the supply chains. So who and what you connect with. Don't rely on the operating system. Yeah, go ahead. Back to your previous slide, point on the bottom. Just out of curiosity, are there any entities or any places where one might find that there's some trusted agency or trusted reviewer who has sort of said, okay, this bit of open source is trusted, or you can trust it, like a third-party reviewer kind of thing? Third-party, okay. Is there anything like that? So the question is there any kind of third-party entity that can pass blessing on whether or not these libraries have been reviewed either for security or just efficacy? Not that I know of, and that's what makes open source so dangerous, is because you really are relying on the person who wrote the code, and we'll go through an example of where that trust got breached, and it got breached pretty badly because we really don't have anything in the open source community, and that's one of the things, like for example the Boost libraries. We'll talk about that in just a minute. There's only one library within Boost that I know that has gone through a security review, and that's Beast. But there are a lot of other libraries like Boost ASIO that we use for networking that really do need to be reviewed for security. Not that there's anybody, one of the nice things about open source is it is open source, and people are going to notice things going into it as long as you've got eyes on that source code. So there's where you talk about the pedigree of the library, the pedigree of the owner, those kinds of things. But there really isn't somebody that sort of looks above it and says, yeah, this has been blessed. It's really up to the library author. Yeah.
You mentioned compilers. There have actually been attacks on compilers as well that modify the code that they're compiling. So your comment about trusting everything below you, the compiler is a case. So
yeah.
Compiler doesn't necessarily mean you trust that.
So the comment is that there have been known attacks on compilers. That's a really hard trick to pull off, and I didn't go that deeply into this. It's not one of it's really rare to do that because you do have these compilers are written by vendors like, I think it would be pretty hard to penetrate into Clang, just because a lot of the developers are in the code every day. But you're right. But you do have to trust the supporters. One of the things that will actually burn you the worst, I think, on a compiler, and we'll talk about that here in just a few minutes, is where does the compiler optimize things out and make your code do things that you didn't realize it was going to do, and that breeds in a vulnerability. Yeah.
I was just going to comment on his comment about tools to
go through your open source.
Mhm.
One tool that our company uses is Black Duck.
Yeah, we'll talk about that here in a little bit.
Okay.
So there are, the comment was that there are tools in order to go and vet your source code. One is Black Duck, and we'll talk about that here in just a few minutes. So when you are connecting to somebody, when you're in an environment, you have to manage your own ecosystem. So what you want to do is you don't want to overly rely on the OS permissions. You do to some level. And the ACLs, you can't assume that those can't be breached. So you have to, for example, when it comes to your config files, go ahead and encrypt them at rest. If you're assuming the ACLs on that file are going to prevent somebody to get to it, they breach the ACLs, that's it. You've got an open file. It's very easy to figure out what to do. But if you encrypt it, it's very simple. It makes it much harder for them to penetrate your system. Verify who you're doing business. Never allow somebody to connect directly to your system if you don't know who they are, where they're coming from. And this is authentication. Most of the time, and we'll talk about this when we're talking about inter-process communication, is we just will take it from anybody who can connect up to that port. So force the authentications on your internal and external communications. Because if we live in a zero trust world, which we do, once they're inside the system, they can talk to you just as if it's your process talking to you. So here's an example of things we don't want to do in our code. You don't want to burn your keys directly into your binaries. And things like shared secrets are really not secret. It's too easy to go with reverse engineering, and we'll talk about reverse engineering in a minute. It's too easy to go and reverse engineer that code and find your shared secret, or you've burned the keys directly in. So what you want to use is you want to use things like trusted platform modules or secure stores, something that holds your keys that's designed specifically to hold them. But when you use those keys, bring those keys in, use them, get rid of them. Don't bring them in at the beginning of your application and have them staying in memory, because then now you're open to side channel attacks like Meltdown and Spectre. But here's a case where the compiler works against us, is that clearing the memory doesn't always clear it. Can anybody think of an example of when that's true? Yeah.
When setting the non-volatile variable that is no longer used, you detect the dead store.
Right, so if I've got a key in memory, and I go and I clear that key and I never use it again, the compiler is completely free to ignore that clear. Which means it's not actually clearing the memory, it's still sitting there. So there are ways to get around. There are actually specific APIs that will go in and actually force the compiler to actually clear out that memory. So when you're using keys or any kind of critical data that's in your system and you're going to use it and you're going to clear it, make sure that you're clearing it in such a way the compiler doesn't optimize that out and then it still stays in memory. So the takeaways. Trusted systems don't talk to untrusted systems. If you've ever worked in a cleared environment, you know that. You'll have two PCs on your desk with completely different networks. One is for the cleared side, one is for the uncleared side. They don't talk to each other. You don't swap anything between them. That's the lesson from the Tesla. System internals are a zero trust environment. What you're talking to in your own software should not be trusted, because you have no way of knowing if that binary hasn't been replaced. All of your memory is eidetic. It will retain itself. If you don't do it correctly, you'll find that in memory, that kind of stuff sticking around on you. Sign and validate your variables. Manage your own ecosystem. Be responsible for the security of your own system. Don't trust or fully rely on the operating system security, the security of your transport layers. These are things that once they fail, they leave you completely vulnerable. Ultimately, you don't own anything. The only things you can trust are the things you own, and most of what you're going to rely on, most of the things in your environment you're going to run, you don't own, which means you don't have the ability to trust them. So this is actually one of my most favorite hacks, and I saw this the other day. Joe Grand, this was a quote from an article that we'll talk about here in a minute. This is somebody who got curious about, is there a way to get an extra instruction set on a CPU that would give you escalated privileges? So his name is Christopher Domas, and there's his Twitter account, and what he was going after was he started going through patents, because there's lots of information you get. So he finds this in a patent. Additionally, accessing some of the internal control registers can enable the user to bypass security mechanisms, e.g., allowing ring 0 access at ring 3, which is bad. In addition, these control registers may reveal information that the processor designers wish to keep proprietary, right, for the very specific reason that that's bad. You don't want people knowing that they can do that. For these reasons, the various x86 processor manufacturers have not publicly documented any description of the address or function of some control MSRs. In other words, they're baking stuff in, they're baking backdoors into their CPUs. Now, this particular one is, it's called Nehemiah, but it's the VSC2, which is an x86 CPU. And as he goes through this list, he's talking about, we really weren't concerned about this because, it's only used in these applications. One of them was medical, and it was like, oh my God, I hope that's not, the device that I'm using. Because he actually finds this. And all of this is right out in a patent. So yesterday when we were talking about reconnaissance, when you're hacking hardware or software, we're going to talk about the reconnaissance of a particular item. In this case, he just finds that this is just a block of text in a patent. So in this case, our security model for hardware is ring 3 is where applications run, so that's us. We're the normal users. Ring 0 is the kernel, that's the golden nugget, that's where you want to get to. And then we've got -1. This is we came up with the ring model before we had all this other stuff, where we only had multiple operating systems running at the same time. So we have the hypervisor, the system management code, and then ultimately the management code, the Q35, that's all management code for the CPU. So MSRs are model-specific registers. If you don't deal in the hardware world, I'll go through this slowly. I don't want to lose anybody because this is actually a really cool thing that he did. So these are 64-bit control registers that are actually, they're addressable. They don't have names. So you'll use commands like read MSR and write MSR. And they're only accessible from ring 0. So you have to have root privileges on that system in order to be able to do this. So how do you find out if those MSR exist? Well, what you have to do is you have to go out and you have to try all of them to see if they actually function. And so he came up with 1,300 that looked like they were viable, where he actually got a response back from the system that it either did something or it didn't kernel panic or it didn't just reset the box. And then he comes up with this sort of stroke of genius, which is a side channel attack. And we're going to talk a lot about side channels here in a minute. But what he wanted to do was he wanted to calculate the access time of all of the MSRs that he tried. The MSRs that are the same are going to have the same access time. The MSRs that are different are going to have different access time. So by going through here and running this side channel attack, which is really just a matter of looking at the artifacts that come from a system, from just poking it, he was able to take it down from 1,300 to 43, which is a huge gain for him. The only problem was that if you do the math, it winds up coming out to be 1.3 times 10 to the 36 instructions, because you've still got to turn it on and then go find out if the instruction exists. In other words, you're poking in the dark. I want to go turn on this, and then I've got to go check and see if any of these are active. And in the meantime, you're going to get kernel panics, or you're going to put the box into reset. So this was going to take forever, but it was this that allowed him to sort of get to the next step, which is just by looking at timing. So he sets up this system, and over here, these are all the PCs, and there's another group on the other side. I'm assuming, I think he had one on both sides. But what he did was he set this up on a laptop so he could run this, and he could scale this up to as many as he wanted. He's got a little control box up here, so he can tell, did the box go into reset? Did it reboot? Did the kernel panic? What happened when I poked that one? And so it took him, he created this piece of software called SandSifter, and SandSifter would go through and let him do this in each of these boxes. It basically is, he's just fuzzing this now. So he finally finds the launch instruction, which is this OF3F, and really it acts just like a jump instruction. It's just jumping somewhere else in the kernel or somewhere else on the chip in order to activate these extra commands. And so he found that the MSR 1107.0 was the one that he called the God mode. It's what turned on the ability to get to these the things you weren't allowed to see, these back doors that they put in to give him all this this extra capability, and within about a week. So when he found this, he activates this, he knows how to get in, so now he can bypass all of the protections that we have in the system. And he actually did this live, which was, his script was fairly short, in fact, sort of horrifyingly short, but he managed to bypass all of it just by finding something that they thought was hidden. This is why obfuscation is such a horrible security if you're thinking obfuscation is going to, it's just the worst technique because someone will figure it out, even if they just fuzz the system. So this leads to a conversation about side channels. So everybody's heard of Meltdown Inspector. Yeah, good, we're not going to talk about that. So this is the NIST definition, an attack enabled by leakage of information from an operational system, characteristics that can be exploited in a side channel attack, including timing, power consumption, and electromagnetic and acoustic emissions. Now they have in here, it's a physical cryptographic system, but I replaced it because it's more general than that. It's not just cryptography. We can get all sorts of side channel attacks and get information about a system that doesn't involve cryptography. So on the hardware, we can look at things like timing. So if you've ever looked at a circuit board, we can tell how many circuits are between one point and another just by looking at the timing of where the impulse goes in and the impulse comes out. Which means we can tell what's operational at any given moment. The same thing comes with power, because power is proportional to not only the number of elements that are in your circuit, but what they are. So capacitors and resistors are all going to do different things. So we can deduce how much current each circuit draws. That allows us to detect what's operational at any one time. So this is what's known as a differential power analysis attack. So we have an RSA algorithm, and here's the equation. We're looking at a spectrum analyzer of this actually in operation. And if you look here, where we spike up here is shorter than where we spike up here. And if you look at the equations, you can see why. So for us, if we're looking to try and decode an RSA key, we watch this running, we can tell where the ones and the zeros are. And that allows us to back out the keys in order to decode whatever it is that they're sending. And this is why hardware attacks are so much fun, because you've got all sorts of equipment you can put in there and you can see things like this, but it also affects software. So this is, we also have what's known as differential fault analysis. So this is kind of like fuzzing. I inject a fault into the system, I want to see what it does. I inject this data in, I want to see the outcome. I'm treating it like a black box. I want to see how this operates by putting data in. Then there's things like emissions. So has anybody heard of Tempest? I know one of you will. Okay, so Tempest is it's a standard that the government sets, especially if you're going to work in sensitive environments, of how much you emit. So that's things like RF emissions, thermal, even acoustic noise. Somebody a while back was able to decode things that were going on in a box just based on the fan speeds, which blew my mind that you could figure that out. This is a thermal image of a board, and what you're looking at is how much work is getting done in these different things. So you've got a chip and a chip, and the fact that this is glowing white hot means either a couple things. Either one, the board is running really hot, so you've loaded this up. Or in the case of the presenter here, he said they found something actually underneath that chip. I'm not sure how you do that, but this is not a BGA. A BGA is where you've got balls here. This is actually where it's got the pins on the edge. But what they were suspecting was that there was actually something operating underneath here because of how hot that was. It was not only the heat of the chip, but it's the heat of whatever's underneath it. So this is a Tempest scan where they were trying to decode what is on a screen. So it used to be that video screens just leak like crazy. I mean, you could, if you had a sensitive enough antenna and you had a good enough piece of software reading that antenna, you could read a screen from yards away and see what was on it. So here's the that's the center frequency right down here. That's the bright band. This is unaltered. This is nothing on there. So it's mostly dark except for the center frequency. But you notice that as you begin to add data into the system, you begin to see these bands. And so each one of these actually has a different pattern. And if you take the monitor and you put a specific test pattern into it and you read these bands and you know what to look for based on the pattern, then you go get somebody else's monitor that has something on it that you don't know. You can use the same process to decode what actually sits on their monitor. So this is why Tempest becomes a big deal. You want to know how much you're emitting. whether it's radio frequency or heat, or in this case, you're giving off energy from your RF energy from your monitor. So, software side channels. Cache data. There is cache bleed, which is an SSL side channel attack, and then we have Spectre and Meltdown. So these are, in the case of Spectre and Meltdown, they're going directly against the autonomic responses of the chip and the hardware and what gives us the speed that we have. But what about concurrency? If I have two things happening at the same time, and it's important that they happen in a specific order, I can now run a timing attack against them to mess up that order, which either gives me information or gives me access. So if you were in my talk at CPUCon last year, I did an attack against an unpatched Linux kernel where I took advantage of their copy on write to do that. That was a timing attack that had been out there for 9 years. I mean, the vulnerability had been there forever. Response timing. Just like with the RSA, the shorter response tells me something, the longer response tells me something different. But if your responses that are coming back from the system now take the same amount of time, I don't have the ability to draw any kind of conclusions from what you're doing on the back end. So even something as simple as going in and doing a password, the password failure should be the same amount of time as the password success. Because what you don't want to do is to be able to do any kind of timing on that operation that tells you what you might be using under the hood. Now, with response timing, it's actually, we do have a benefit with having an operating system. So a preemptive multitasking operating system is going to give you all sorts of variations in your system. So response timing is much harder to run in a software system. But the concurrency is actually fairly easy. If I know that they've got two things running in concurrence, that's one of the places where I'd want to attack. So when you're going through and you have something in it where you've got concurrency in your system, make sure that concurrency is well protected so that you don't have the kinds of problems that we found in the copy on write on a Linux kernel. Memory. It's hard to run buffer overflows. They're not impossible at this time, but they're really hard to do the traditional buffer overflows. But what we can do is, because stuff is out on the heap, if I can overflow one buffer into the next buffer, the system isn't going to say anything about it. It might not even notice that it's happening. But if there is control flow within your system that's operating on the state of that second buffer, now all of a sudden I've altered the control flow. One of the things that I see in code every once in a while is a code pointer fault, where I've got a struct, it's got some memory, and then somewhere it's got a code pointer, where I'm going to point to a different place to begin execution. If I can overflow that buffer into the code pointer, now all of a sudden I can alter the program flow. That's easier to do when you're talking about something like open source, because I can actually go see it. Holding in keys in memory after use. The longer those keys stay in use, the easier it is for me to get them. So we talked a little bit about making sure that you get them out of memory as soon as you're done with them. And then data type conversion. Undefined behavior is a significant problem in C++. And I hear a lot of conversations of, well, it really needs to be defined. Oh no, just make it undefined behavior, as if there's no implications to just saying, well, if you've done it wrong, then like on contracts, what happens? I had a conversation with Michael Case yesterday. What happens if you violate a contract in the interface? What should that be? Should that be undefined behavior, or should it be you should use accept it and sort of go on and note that it happened? Making it undefined behavior means it's something that you can go in and take advantage of. So we talked about Wi-Fi a little bit. It's really easy to sniff Wi-Fi traffic on a promiscuousness. Get that. Now all of a sudden you can begin putting the packets together, and that gives you all sorts of time to go and see if you can break the encryption, especially if they didn't encrypt the packets and you've already gotten past something like the WPA. So WPA has already been broken, don't use that. WPA2 has already been compromised. This is key reinstallation attacks. There's entire software groups out there, software packages out there that are specific to running crack attacks against WPA2. So this is, again, why you want to encrypt yourself and use something like AES encryption. Don't use something cheap or do obfuscation. I see that a lot of times, especially I've seen people like with video data and they flip a couple of bits and they think that's going to make it safe, and it won't. It's too easy to go figure it out what that is. Network traffic. Analyzing the network traffic has sort of become the next big thing. And there's an article out there just within the last few weeks about Netflix and what happens. I don't have Netflix, so I didn't fully understand what they were talking about, but there's the ability to go in and make selections, and it's either you're doing ratings, and depending on what you select, something else comes back, and it'll either come back with the default or it'll come back with something different. Well, they could now tell the difference of whether or not somebody had actually made it as a choice or whether they were getting the default by the size of the packets that were coming back. So side channel attacks are really just the ability to derive information from the ordinary operations of your system. If you're going to be doing something like that, make sure the packets are the same, at least the same width. And that way there's nothing, I can't go in and run a statistical analysis against your data to look at things like response times, sizes, those kinds of things. Logging is a huge problem. Anybody here in the embedded world? Yeah. So what's the first thing that we start throwing in the logs when the board comes up? It's all of our registers, all of our memory maps, because we need those. And I see this even on commercial products that are shipping, where I go tap into their serial port and suddenly I'm watching all the traffic, and now I know exactly how your hardware is put together. I know where I need to go and exactly the places where you're vulnerable. So you've given me a map. One of the things that we put into is we put in account information. So if in your logs you're putting in any of these things like function names and templates, those are great for us. If you have debugging logs, great, put those in, because we need those to know program flow. But nobody outside of the development team needs to know that. So you ratchet up your logging so that when the logs are sitting on the endpoint, remember, you can't trust the ACLs, those can be broken, and you don't want them getting the logs and being able to watch the control flow of your system. And then if they can play with it, then they really have an opportunity now to go and play with the control flow to see how your system works. Configuration information. Don't put it in the log files if you have configuration information. I know it's easy for us, because then we can go and look at the logs when we need to diagnose something. But it also gives somebody who's wanting to get into your system invaluable information. And then the last was the hardware setup. Error messages. I will sometimes see people putting account information in their error messages, or pathing to critical files, or configuration information. None of that should go into an error message. That's just really easy for me to take advantage of once I get to that. So this is going to be sort of a sensitive topic, because one of the things that makes open source work is the licensing schemas, but the licensing tells me things. So there are some licenses, like GNU and Mozilla, that require me to submit back to the repo if I've made changes. So I've had instances where we were using BusyBox, it was an embedded development project, and we needed to go in and make changes to the device drivers. So now the question becomes are the changes that we're putting in, do they require us to go back and resubmit that to the repo? And in this case, I think the license requires that you have to make the source code available, the entire set of source code. Well, does that include my device driver too? Does that include what uses the device driver? Now all of a sudden you've got a legal question, and open source libraries are now starting to push back against people who violate their licenses. So the Software Freedom Conservancy is the host of this conference, is actually one of those organizations that holds people who uses open source licenses accountable for when they violate the licenses. So you have to be careful if you're going to use things that require you to either submit back to the repo or make that source code available, because that's what I want. If I can call you up and say, I want the source code for this particular part of your system, and you are obligated to do this because of licensing, that's wonderful. You've just given me your source code. And now you get into a legal battle of this. How far does that extend out in your product? Licensing that requires attribution. OpenSSL 3.0 has changed a bit. It used to be a bit different, but if you're using GNU, Mozilla, Apache, or MIT, all of those require you to, and the BD is the Bloomberg development libraries. They require me to tell everyone else that I'm using that license, which makes sense. I mean, if you're using somebody else's license, you have a responsibility to sort of say, hey, we're making use of it. But when I want to penetrate a system, knowing that you're using specific versions of these, or even knowing that you're using those packages, gives me a lot of information that you probably don't want, because I've got the source code. And now I can go after the source code and see whether or not there's a way for me to get into your system using something that's in there. So a side channel is going to be something that can target anything that you leak. Any information that you leak is something I want to take advantage of. So we need to understand using open source, not only from a security standpoint of whether or not they've been, these are things that have been reviewed, but also the fact that we're using them. Censor your logs and error messages. If it's not information that the user needs, if it's not something that you have to have in a log, don't put it in there. Put it in the debug, ratchet up your logging levels so that you're not running at a debug level when you're out in the wild. Limit the external emissions of information. There are some, and this is probably a longer conversation and different, where you can actually make errors in your code that actually leak information like address space information. Try and be uniform in the way you do your responses in terms of the timing and the sizes, because that takes away someone's ability to gather information. Don't rely on first-line crypto. Once it fails, you're totally exposed. It's one of the best hacks I've ever seen. We talked about it in Aurora yesterday. It had been encrypted multiple times before it ever got put down to the box, and they just unwrapped it. It doesn't cost that much time. And then limit the amount of sensitive data when you bring it in and how long you keep it. Any questions so far? Yeah.
How would you feel about like asymmetric cryptography of log messages, so that your logs are decrypted?
So so the question was, how do I feel about asymmetric encryption for logging messages? If you're dealing with a specific, this process is generating the log, this process is the one that's writing it out, yes, I mean, that makes perfect sense. I don't know where the benefit of actually using asymmetric encryption on the log itself.
You can then extract the log and take it and read it somewhere else for debugging purposes, but without.
Well, yeah, absolutely. I mean, you want to write that with one key and then read it with the other, because you want to make it so that you can't. Exactly. So you write it with a public key and you read it back with a private key.
That would address your in a different way without having to necessarily remove very useful.
Right. Now, here's the problem with logging is that depending on the logging level, you're going to be spewing a lot of data out. And I don't know about you guys, but I've always had a problem with my logger consuming too many cycles and getting behind.
That way, but maybe certain ones.
Yeah. So if you don't feel like you can encrypt it, then just limit what you put into it. And think about, well, can I use this to gain information about the system that I, as an engineer, do I really need it in there? A lot of times we put stuff in our logs, we just don't need it. It's just convenient. Or we ship with the debug turned on, and so we're spewing information out that's just really valuable for everybody else. Okay, so let's talk about DigiNotar. Anybody ever heard of DigiNotar? So this was a Dutch certificate authority, and the way things work is that if you're a certificate authority, you actually have to go to the major browser manufacturers, and you have to get certified as being a CA, and then you're in their trusted CA areas, and then whatever certificates that you issue, they will actually honor in the browser. So in this case, somebody got inside of DigiNotar, and they created something on the order of about 500 fake certificates. And then there was this line here at the end that said, I will sacrifice my soul for my leader, written in Persian. Anybody know where Persian is spoken? Yeah, 2 lines up, it's Iran. What they found was these were used to run a man-in-the-middle attack against about 300,000 Gmail users in Iran. Now, it takes more than just getting the certificate corrupted. You have to do what's known as DNS poisoning, which is I have to be able to replace the real Google record with my fake Google record, and then it points to a different place in the internet, and then I can watch what people do when they log in, and you gather credentials or see the kinds of things that are going. They had this great security. They had layered. They were doing everything right. You had layered security from beginning to end. All the certificate services, the servers were all isolated. In fact, they were in this room that was kind of like the Mission Impossible, where he's hanging from the ceiling, and you had things like you had to have a palm print to get in and a card to get in, and then you had to have a card in the machine, and so their security was really top notch, sort of. They had an unpatched website that they didn't realize was was there, which was the point of entry. But then the biggest problem was here, was they went and they left the key card in the server. And that was, and I don't think it was malicious, it was just they were trying to make it so that they could do certificate revocations very quickly, because the same server did both. And once they did this, they pretty much, that was the game. They're going to get in, but that was sort of the last line of defense that they had, was the physical security. So, and by the way, they had to declare bankruptcy, and did you know Tor doesn't exist anymore. So let's talk about physical access. So there's different ways of getting in. There's non-invasive, which is I want to look at the protocols. I want to go and look at the debug ports. Somebody yesterday mentioned JTAG ports on one of the first things to do is take those off. Then there's physically invasive, where we have fault injection, whether you're just putting spurious noise on the line or you're actually putting in real faults in a fuzzing capability. And then there's decapsulation. So when we talk about reverse engineering a PCB, the first place you want to go is if there's data sheets available, because that's the easiest. I mean, they'll tell you exactly how it works, where are all the registers, how does the voltages, things like that. This is an example of X-ray computed tomography. So what we want to do, and these are not like X-rays in hospitals, these are like small X-rays at a PCB manufacturer that they use for testing boards and doing spot checking. So what you can see here is these square pads. These are going to wind up being BGA chips. So the chip, instead of having the teeth that are on the side, they've got a whole matrix of solder balls on the bottom, that's the connections here on the bottom. There's another one up here. But what this does is, because you have a layered board, you don't always get to see the traces, but because I've got an X-ray of it, now I can see all the traces and how everything is put together. So that tells me how the system works. This is decapsulation. This is just a CPU that someone came in and just sliced off the top of the CPU, and now you can see pretty clearly everything that the CPU does, all the different structures. Between that and the data sheet, you can pretty much decode this one to figure out exactly what that chip does. Interface analysis, when we're reverse engineering, there's a really cool little piece of equipment called Bus Pirate. If I don't know what that bus does and I go hook up to it, it'll help me decode the signals on that bus to tell me, is this a SPI bus, I2C CAN, something like that. And then what you do is you take a digital analyzer and you hook it up to that bus, and it's got its own protocols built in, and then now you've decoded the information. Because nobody in hardware does anything to obfuscate or encrypt their traffic across their buses. It's just not worth it. Connector repopulation. This is actually your piece of Netgear equipment. This right down here is the JTAG port. What they'll do is they'll take that off on the production boards, but they'll leave the pads there. And unless they burn the fuses out, I think it's the E fuses for these, you can go back and repopulate that, just with a soldering iron, and now all of a sudden you've got access to the JTAG port. So we want that because we want to read the firmware. There's also, sometimes you'll have a single wire debug port on there, but then the serial ports are the ones that you want to look at, which on here is, now I can go watch the boot up sequence. Can I interrupt it? What are they loading? Are they using U-boot? Are they using BusyBox? What are they bringing up in the system, which tells me information about how that piece of hardware is put together. So for firmware analysis, we want to know what information these guys provide. We want to, they will give out a lot of information. The first place you want to go is things like patents and places like the website. See if you can find an open FTP site to see if their engineers have gotten lazy and they have all their design documents back there. That's always nice. Go put Wireshark in there and watch the update. So when they're doing an update for the firmware update, well, you just grab that right out of the air and then save it off, and there you go. It's nice to know what OS version they are. If you're BusyBox 2.1, well, I know what vulnerabilities are in that, so if that's what they're using, now I know places where I can go and attack them. It'd be nice to have the device tree blob, which is going to hold the operating system and the file systems. I want to know if they're using U-boot, CramFS, which are all actually pretty common. And so some of the tools we'll use are things like binwalk, DD, strings. What we're looking for is printable characters, which tell you things that, you know, in binary, you can't tell they're printable characters, but as this goes through, it'll look and find and just pull out all the strings, which gives you an idea of control flow and things that they're doing. So on software, how does this apply to us? If you want to penetrate into your system, the first thing is vendor information. Go to their website. Find out what they have to say about their system. Look for open FTP sites where they might be having updates, or they've got information that they don't realize they've exposed. The dark web, depending on what you are. If you're a major infrastructure company like Google, Adobe, Facebook, Amazon, you're going to find all sorts of information on the dark web specific to those companies and their software, where people have gone in and done this analysis, and it gets you a little further down the road. Log files, again, I know we keep coming back to this, but we're really chatty in our log files. Once I have those log files, you're just giving me a roadmap to reverse engineer the way that software works, especially if you're putting in things like function names. That makes it really easy, and I'll show you a piece of software where you can do things like that. So configuration information, function names, keep those out of your logs. Then system artifacts. Don't use the registry. If you're writing code that works, it's multi-platform, you're not using the registry anyway, you're using your own config files because it doesn't exist in Linux. But the problem with the registry is it's pretty much open to anybody to read. You have to have it that way, the operating system doesn't work. But putting stuff in there just means it's easier for me to go figure out what you've got, and then I can go play with it if I've got write access to your registry keys. So the binaries. Anybody ever shipped the debug versions of their binaries? Because I've seen it happen. It's a mistake. It's an oversight. People will do that. Sometimes they'll do it because they think that memory's padded differently in a debug version, and so they want the debug build, especially when they're first coming out with their product, just because it gives them that added protection. And maybe they've got some debug code in there that they want running while this is going out in the first couple of generations. That's really easy for you to go and reverse debug. Make sure you strip out the symbols, obviously. Don't bake your crypto keys into the binaries. Don't put shared secrets in there. Shared secrets are not secret. The thing with decoding things this way is you have to have a pretty high level of assembly knowledge. The good news is almost everybody in here, because you deal with C++, you're probably in Godbolt a lot looking at the assembly code. So it's not that hard. It just requires a special talent. Some of the things that we use to debug binaries are going to be strace, ltrace, dtrace. IDOPRO is actually really cool. I'll show you that in just a second. Then there's this thing called virtualor. I can't pronounce it. Gal Zeben, I saw a presentation on her the other day. She's building a system that can rebuild the virtual tables. So one of the problems with C++ is you've got all these vtables running around, you've got all these pointers going to everything. Well, if you can rebuild that, you can rebuild the classes, which gives you a lot of information about what that does and how to get into it. This is IDOPRO, and it's actually pretty cool. This is an integrated system. It's kind of expensive, but it's an integrated system that goes in and it will tear apart a binary, and it will tell you things like, one, it'll pull out all the relationships here between the functions. It'll go out and tell you what system libraries are being used in that binary, pulls out the strings for you. So it's like all the really cool tools that you used to have to use to do things like this, they just like built it all into one. And the primary purpose of this is to pull apart malware. So security researchers will use this. People in the government will use this in order to investigate malware when it gets caught. But if you've got the money, you can go do that too if you want to. If you're in that industry where you're trying to penetrate people's systems by looking at their binaries, you've got the money to do this. It's actually a really cool tool. IPC interfaces. Anybody here ever do anything to secure their IPC interfaces? Yeah, I mean, nobody does. I mean, maybe you might obfuscate it, you might do something a little, but we always think of, no, we really can't do anything because we need the speed. Well, that's a great place because your IPC interface, if you're using, whether it's protocol buffers or something else, that's a really great place for me to go in and start a fuzzing attack so that I can look at the condition responses of your system. I put this in, what does it do? Can I crash it here? Do something, specifically authenticate your traffic. Don't just accept IPC traffic from somebody. You may think you know who it's coming from, but it's too easy to run things like man-in-the-middle attacks or replay attacks. So if you're encrypting it and you're running it with session keys, now all of a sudden you don't have that capability. Yes, it does have some overhead associated with it, but it is also much more secure than leaving that thing open for anybody to talk to. Protocols. The biggest thing here is the last line is treat your protocols like they're intellectual property. You do not want you want to make them have to decode the protocols. You don't want them to be able to figure out the protocols because it's published or because it's in the logs. I see this a lot of times in logs is they'll get some sort of a message over an IPC and they'll just write the entire message out. Well, I guess it's good for debugging, but the problem is it's also really good for me because now all of a sudden I know what your protocol looks like. These just allow people to know the sources and methods of how your stuff is put together, and it's another side channel leak that can do. Command line interfaces. Does anybody ever do this in their system, especially on the hardware side? Yeah, don't. Don't ship with these. I know they're good for developers. They're really good for your engineers in the field. But the problem is they're also really good for people like me who will go in and use them to mess with your system. So we don't ever secure them in any meaningful way. What's the first thing you do when you type the binary that's got that is your command line utilities? Well, it just spits out the dictionary of all the things that it can do, and it just makes it easy for people to get it. If you have to do this, because these things go in at a high level, because they're not authenticated, because they're easy to use, because they're like gold for somebody who wants to penetrate a system, these are the kinds of things that should be, if you have to have them, you don't ship them on the box. You actually give them to the SEs. You have them. They're on a separate stick. They can run them off USB or something like that if they have to, but they're never physically on the box. That's just really easy to do. So what are the most important things? Yeah, obfuscation is always a bad strategy. Don't ship your CLIs. Really, it's a matter of asking yourself, do I really need to do this? Do I really need this in the logging? Do I really need to have this built into the binary? So most of these are just sort of the common sense things that you do, but we don't think about it because we're not thinking about security, we're thinking about building a system that works. So this one is really controversial, although it's really cool. So the Supermicro supply chain attack from 2015. Bloomberg was the one that sort of blew the lid off of this thing. What this was is that, and I've used, the military uses Supermicro a lot. So there was this, what they did was they found a piece about the size of a grain of rice on, and this was a rack mount server, so it had the slide-in cards. And what they did was this company here, according to the article, this company here was in the process of being bought, and during the due diligence, they found this little, and Elemental does video processing. So what they did was they found this, according to the article, when they were doing the due diligence, and this wound up going, as you can see, it's spread out to a lot of different companies. Some of the things in the article really didn't sort of gel, especially if you know how the hardware works and some of these things, but what's interesting is this last part. This piece got put on the board, which supposedly opened a back door. The problem is the companies that were mentioned in the article just straight up denied it. And that's pretty rare for a company. Usually, I mean, there's no safe harbor for a straight up denial for a public company. So if you have something like Apple saying, yeah, it never happened, this is totally wrong, the article's totally bogus, that's sort of hard to get past. But Bloomberg has stood by their reporting. And I found this graphic on their article, and it's really cool. If you watch this thing, as they're delayering this, it's right there. Now, besides the fact that it's a really cool GIF, is this true? I don't know. There's enough uncertainty, but the fact that you've got both sides digging in and saying, yes, it did happen, or no, it didn't. The bottom line is things like this have happened before. If you've worked in the military anytime in the last 20 years, we have been through things like this where we have had those kinds of things happening. And then I love this quote from Joe Grand. It was actually part of the article, as was the other one. It said, having a well-done nation-state level hardware implant surface would be like witnessing a unicorn jumping over a rainbow. I mean, it's absolutely right. I mean, this is just, if this is true, this has got to be like at the very top hacks that you could ever do. So let's talk about supply chains, because this is where this got introduced. So if you want, in a hardware sense, if you want to interdict or get into a supply chain, there's a couple of ways you do this. One is interdiction. The boards are created, they're shipped, I catch them, I make the mods myself, and then I send them on to their destination. So this requires a lot of technical capability because you're modding a PCB that's already been fabbed, and it can be very difficult to do this. Sometimes it's just a matter of replacing the firmware. We saw a lot of firmware coming in military circles that had, extras in the firmware that was stuff that wasn't supposed to be in there. But it's very difficult to pull off. It also is the one where it's the sneakiest. It's the one that's hardest to detect. So spy agencies have a tendency to like to do this. Then there's seeding, and that's what the Supermicro one would have been. Is I've gotten into the manufacturing process, which means I'm putting this in at the manufacturing level. We saw this with Seagate a while back, where there were some drives. There was somebody that was working for a nation state, actually at a manufacturing overseas, and they were putting things into the drives that were there to compromise. And so anybody who used that drive, it was easy just to get their data off. This requires you to compromise the manufacturer, so obviously it's much harder to do from that perspective. But then it is sort of easier to do technically, because really what you're doing is you're changing the architecture before it's ever fabbed. So one of the ways we go when we look at things like this is and try and catch these things is do random testing. So it's like a baker's dozen. So you get a million units, you go pull random lots, you test them to see if they're there. On-site inspections are another way to do it, and then monitoring for spurious signals. Like, for example, if you have this thing under test, are you seeing any other kind of signals coming out of this? Or is it trying to connect up to things that it shouldn't connect up to, which might tell you that it's got something on that shouldn't be there? So the problem with random testing is that most of the time I don't have to do all of them. I just need to do 5%. So 5% on a million is 50,000, which means I'm still getting a pretty good return on it. It's just really hard for you to find that 5% in that. I mean, you have to be really, really lucky or just very good to find that. On-site inspections, anyone smart enough to do this, clever enough not to get caught, that's actually pretty hard, and I haven't heard of anybody getting caught doing that. They usually get caught through other means. And then what does it mean to look for anomalous behavior? I mean, there's no way to know when that behavior is going to crop up, what form it's going to take. And then we have beaconing. I talked about this a little bit yesterday. So beaconing is a case where I've put my malware in, or I've compromised your system, but I'm not doing anything immediately. I'm just waiting. And every once in a while, I'll send out a beacon and get a response that says, yeah, don't do anything right now. We're going to wait. So I can lay low for a while in your system. You won't know that I'm there until I actually start doing something in your system that triggers an alarm. So that can sometimes, that's a way of defeating monitoring. So let's look at software supply chains, and our biggest one is going to be our open source. So have we code reviewed the open source libraries that we use? Do we trust the authors of those open source libraries? Do we even know the authors? Has that particular library been code reviewed for security? And it's when I talked about trust being organic, code reviews are organic too. It's not just, okay, at this point in time, it's all good and it's blessed. Well, you're changing the software as you go. If you're not making that a continuous process, then at some point in time, you lost the benefit of the initial review. Closed source, we really care about the company. We really care about how they're looking at their trust, because remember, we don't have any insight into it. We're just using a binary that somebody's giving us. So here's an example of what I'm talking about. So if anybody does JavaScript programming, this is the event stream. So this package is for Node.js. It had about 2 million downloads per week, which is a pretty good clip. What happened, though, was the original author sort of got tired of maintaining it, because this is all free. It's free to everybody else, but it's a lot of work on his part. So he transfers this to somebody with that handle, and he had no idea who that person was. Didn't vet them. Just said, yeah, I'm totally cool with you doing this. So he adds a dependency to another library called FlatMapStream, except FlatMapStream had been modified to go steal bitcoins. And he was going after a very specific, in this case, he was going after BitPay's copay wallet. The problem is if you code review event stream, you're not going to see anything. I mean, okay, he's added a library, but unless you follow the chain down and go look at this, which is what somebody actually did when they noticed weird behavior, they finally found that, oh, this is what's going on. But the place began as you had the original author that everybody trusted because he'd been maintaining this for years, but then he suddenly transfers to this guy with no notice, no warning, and nobody who uses this even knows it. So unless they know the person, unless they're following up, they have no way of knowing that. So if you use this library, you became a Bitcoin miner or stealer, however you want to put it. So this is an example of somebody who tapped into the supply chain, and a lot of companies got burned by this. And this could have been worse because this is what they were going after. Well, what if they're going after other things? What if this thing that's running in your environment is scraping credentials so that you can now get back into that environment sometime later? So this is an example, and it's very recent. It's this past year of something that happened in our supply chain that nobody noticed. So third-party libraries, they're not free. They do have a cost associated with them. I know they seem like free, which is why they're attractive, but they do have a cost. They're generally unsafe, but they're everywhere. So one of the things that we have to begin as an industry looking at is the question somebody brought up either yesterday or today about, is there an entity or is there a way that you can find out if these are trusted libraries? Boost is one of those things that's ubiquitous. I brought up Beast has been security reviewed, but as far as I know, nothing else has. If I knew you were using Boost, that'd be a nice big target for me, especially if you're using something that's sort of on the outside, like Boost ASIO. So one of the things, there's the Boost Steering Committee on Friday, I was going to talk to them about, is this something that they're willing to do in their environment, which is, you can't do the whole thing because Boost is enormous, but you can start with the stuff that sort of is at the outside edges. And begin going through these kinds of security reviews and doing them continually as code is changed so that we can ensure, not that I think someone is going to be, oh, there's too many eyes on the Boost libraries and the owners are very focused on the library, but do they know, have they looked at this from a standpoint of security? So code review your third-party libraries. In this case, for example, we've had several open source bugs or vulnerabilities in OpenSSL. And that's a big one, because if you can crack into OpenSSL and everybody uses it, you've got a lot of things you can do. So I think as an industry, prefer the libraries that have been code reviewed. Don't use precompiled binaries. That was sort of the problem with what he did on the event stream package was, if you looked at the code, he had removed it from the code, but when he compiled the binaries, he put it in. So if you looked at the source code, it wasn't there. It only showed up in the binaries. So that's part of the problem with using precompiled binaries is that you don't really know what's in that binary. Unless you build it from source, you just don't have the way of knowing. Invest in code scanning products. We'll talk about a couple of those in just a minute. What I would do is if you find a security vulnerability or some sort of major bug within a library is go ahead and submit it directly to the authors offline and then give them a certain amount of time to get it fixed and get a patch rolled out, because if they don't take it seriously, then it's just sitting out there and other people are going to potentially get burned by it. Give them 30 days and you don't announce it to the world. I don't think any library author has a problem with that except the ones that are lazy and don't want to fix their stuff. Test your third-party libraries. If nothing else, you can put the library in isolation and just look for hardware traffic. Are they hitting the hard drive for reasons that you don't really understand under normal use cases? Are they trying to connect to things on the internet? Are they opening ports? Are they doing something that's unexpected? That's a good way to sort of put them into a test environment and see how they behave. So the takeaways. You're only as strong as your weakest third-party library. Those defects that are in the third-party libraries are your defects. You own them. And in the same way that you would want to deal with the defects that are in your own code, you don't have to accept what's in somebody else's code. Never assume that your supply chains are secure. This is especially on where people are just downloading binaries. That's going to become a bigger problem than we've seen. This is probably the biggest one when you're security aware. It's kind of like teaching people about anti-phishing. Once you teach people what looks suspicious, the amount of phishing emails that that actually get tripped, it starts to go down. They don't fall for the scams as quickly as possible. Same thing with code reviews. When you begin teaching people how to do code reviews and you begin knowing what to look for, suddenly these things begin to sort of stand out like beacons. And then here's what we were talking about before, Black Duck and White Source. Those are two products that are there to, they vet third-party and open source libraries. The other thing they'll do is they'll tell you about the licensing requirements, and they'll tell you if they'll go in your environment and look at what you're using and then saying, oh, you're 3 revisions behind, and by the way, there were security vulnerabilities in this, so you need to upgrade. So these are actually pretty good things to put in your environment. They're a little expensive. Questions before I go on? So for CPBCon, it is coming up pretty fast on us. If you would like to volunteer, this is the URL to go to. So if you're local to Denver, because we've moved to Aurora, please volunteer. You'll get to see the conference. You'll get to see any talk you want, and you'll get to see the conference from a side you don't ever normally get to see. And then if you are not in town, you can come, and we have a grant program which will help defray the costs of your hotel and your travel. So you can volunteer from outside. And people who do volunteer, you get free access to the conference for the entire time, plus you get vastly reduced costs on the pre- and post-conference training classes, space permitting. So at that time, at CPBCon, after the conference, I'm going to be teaching a class called Exploiting Modern C++. This is actually not really part of that class, but it does sort of inform it. What we're going to talk a lot about is, sort of in the context of security, is how do you write secure code, but how do you write high-quality code? Because high-quality code is 85% of the way to being secure code. And if you don't have high-quality code, if you haven't architected the code right or the system right, it'll make it very hard for you to make it secure as you build it. So we're going to talk a lot about the architecture. We're going to talk about how to do code reviews, what to look for, the kinds of things we often miss in our code reviews, and then look at testing. How do you properly test a system from a security standpoint, which also makes it a much stronger, more stable system. And then I have, my first book will be coming out in the spring of 2020, so keep an eye out for like Amazon and other booksellers. This is actually going to be sort of a primer. You can walk into this with knowing nothing about security. So we'll walk through what are the security issues. There's a huge section of just on code reviews, just on the kinds of things in C++ that tend to trip us up, that tend to make our code less vulnerable. How do you test it? Which types of testing will uncover which bugs? So it's kind of like the written version of the training course. The training course is really hands-on and instructor-led. This is sort of, okay, we're going to spend a lot more time talking about things like threat modeling and testing and how you produce high-quality code that is also secure. Any other questions? Yeah.
That sounds interesting, but I'm almost certain I'm going to forget about it. Do you have a notification email list or something?
So,
while we're thinking about it?
I don't have a notification list, but I keep everybody informed of what's going on here on madphysics.com. So it's madphysics with 2 Ds. And then you can always, there's my email, and then I'm on CPP Lang all the time, so that's my CPP Lang, my Slack handle. Anything else? Okay, you guys have a great day.